G'day guys, welcome back to part 3 of our work energy formula proof. In this particular video, I'm going to be spending a lot of time talking about elastic energy. Okay, so remember where we left off. We were talking about a particle of mass m, and we said this thing was swooping out some complicated path because we had a whole bunch of forces on it. We had a force here and a force here and a force here, and I kind of left you on a cliffhanger. I told you that the following video, which is this one, would be focusing on the work done by a spring, right? So if we were to take this force as being the force from a spring, what is the work done by that force? Well, in order to do this in a realistic time, I've decided to simplify the problem to a one-dimensional problem. Let's imagine that we have a particle just here, and let's say that we have our axis just here, our one-dimensional axis, and let's say that this is the distance x from our axis to our particle at any particular time. Now let's imagine that this particle is also connected to a spring just here. Okay? And by the way, guys, I know I'm kind of copping out a little bit by solving this, by showing you how to do this in 1 dimensions. Rest assured, this can be generalized to 2 and even 3 dimensions. Okay, so we've got our particle, we've got a spring. What's the force on the particle from the spring? Well, from Hooke's law, we know that if the spring is elongated a distance L, then the force on the particle will be KL this way, right? That's just Hooke's law, where K is your spring constant, right? And to make that abundantly clear, I'm saying that L is the amount the spring has been stretched from its unstretched length, L naught, right? Okay, great. So now we've got to find our work done by this force, right? So let's use the definition of work. We know that the work, in this case, our work done by our spring force, is going to be equal to the integral of F dot dr. In this simplified one-dimensional case, this becomes quite easy to analyze the dot product. This just turns into the one-dimensional integral of F dot dx, which is going to be KL dx, okay? Okay, well, what's this? Well, we need a relationship relating x to L, because you betcha they're not the same thing, right? So, what are we going to do? Well, we can generate an extra equation by realizing that there's a fixed distance between our axis and our wall containing our spring, right? So I'm going to call that fixed distance capital X, right? And notice it is a fixed distance. It doesn't matter where our particle is, right? The wall's not going to move, so this distance will remain constant, right? So as a result, I can say that, in fact, I'll write it over here, I can say that capital X is going to be equal to this distance, which I will call, I'll call this X, right? Plus these two distances, plus L naught. Notice I've just said this distance is equal to this distance plus this distance plus this distance, right? And we can actually differentiate both sides with respect to x now, and realizing that the left-hand side becomes 0 because x is a constant. The right-hand side becomes 1 just here because x is our variable. Once differentiated with respect to x is just 1. And this right here is quite interesting. This turns into dl dx, right? And this turns into 0. Right, notice this is dl dx because you better believe it, as this particle moves, so as x changes, L will change as well, right? So, but L naught won't change because L naught is just a constant. It's your unstretched length, okay? So that's what this equation turns into once you differentiate both sides. You can prove by rearranging this formula that dx is just going to equal to negative dl, right? You can do that by arranging the 1 and doing the algebra and treating this differential as a fraction. A little bit of a math fudge, but okay. Now we can finish solving this integral. Well, we know this will boil down into, let's figure it out. It'll be KL times by dx, which is going to be minus dl, right? And when you solve that, you can bring out the minus and the k. It'll be minus k times the integral of L dl. Notice that our limits of integration now must be from L1, the amount the spring has stretched from the particle's first position, let's say from here, right? And L2 from here, which is the amount the spring has been stretched from the particle's second position, right? This becomes a quite easy integral to analyze. This will turn into minus k times by L squared on 2 with limits from L1 to L2. And of course, if you were to analyze that, that will become minus a half K L2 squared minus L1 squared, right? And this is our work done by our spring force. Now, obviously I've only proven this for the one-dimensional case, but rest assured, guys, this can be generalized to 2 dimensions and 3 dimensions. You just need to involve something called conservative force fields, but the maths is quite heavy, so, and rest assured, it's not as interesting as it sounds. So, there we go. I'm just going to prove it for the one-dimensional case. Alright, now let's bring this back into the bigger picture. Remember, before I was talking about our particle just here, and we said it was swooping out some complicated path, and then I kind of left you on a cliffhanger. I said that the work done by our force 2, in this case our spring force, plus our work done by this mysterious third force, is going to be equal to our change in kinetic energy plus our change in gravitational potential energy, right? Oh, spelt it wrong. It's gravitational potential energy. Get the acronym right. GPE, right? And just so you're clear, this was what I called F1. This is what I called F2, right? F2 in this case is our spring force, right? And F3 just here, okay? Well, we can substitute W2 for our spring if it's true that F2 was our spring force. So we can say this becomes minus a half K L2 squared minus L1 squared plus W3, so our work done by this mysterious force, which I haven't described yet, is going to be equal to the change in kinetic energy of our system plus the change in gravitational potential energy. And of course, we can bring this to the right-hand side, and what we're left with is, let's see, we're going to be left with W3. W3 is going to be equal to our change in kinetic energy plus our change in gravitational potential energy plus a half K L2 squared minus L2 squared minus L1 squared. Okay, now we're almost done. I'm going to define something called elastic energy now. So I'm going to define something called elastic energy, and I'm going to define it as a half times by a spring constant times by L squared. So basically I'm saying if there's a spring acting on your connected to your particle, then by definition the elastic energy, whatever it is going to be half times the spring constant of that spring times the amount that spring has been stretched squared. And you might see why I've defined this arbitrary thing this way. It's because we've got something in the form of this. And like we've done before, we can now say, and let me write it back to right, it's going to be our change in kinetic energy plus our change in gravitational potential energy plus, let's see, it'll be our elastic energy at point 2 minus our elastic energy at point 1. In other words, that'll boil down into our change in elastic energy is going to be equal to W3. Okay, so this is what we've worked so hard to achieve this entire time. This is our complete formula. Now, I thought I could have done it in this video, but I guess I can't. I'm probably going to create a fourth video to define some more terms, something called mechanical energy and conservative and non-conservative forces. So I won't do it in this video. Sorry for misleading you. There will be a fourth video where I'm going to be talking about this formula in a little bit more detail. Cheers, guys.